Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture of robust control. So over the past few lectures, we've been analyzing or trying to get a handle over this H2 optimal control problem, the synthesis of the H2 optimal controller. Contrary to conventional approaches which approach it from the optimal control perspective, we've tried to give you an algebraic flavor for the problem, and in today's lecture that same approach will be bolstered even further when we'll not just look at this Riccati equation based approach that involves these Hamiltonians, but we'll also give you an LMI formulation of the same problem and a way of solving this problem using LMIs. Okay? So although I must tell you that the next problem we are going to look at after this one is over, that is the H infinity problem, where we shall be entirely dealing with LMIs. This H2 optimal control problem need not require going via the LMI route. Nonetheless, just to give you a unifying flavor that, well, the H2 optimal control problem can be solved using this Riccati operations and the Hamiltonians that we have defined, but also they can be solved using the LMI approach. So once we are through with both the H2 and H infinity control synthesis problems, you will see that the LMIs indeed are a very powerful tool that allow you to solve a plethora of problems, and within the ambit of which H2 and H infinity are just two examples. Right. So the overall goal, to summarize what we are trying to do here, is we've first seen this internally stabilizing controller, the family of all such controllers. We've seen this Euler parameterization prior to this. Now we are looking at H2 optimal control problem, and we are going to also see how it can be solved using LMIs, a convex optimization formulation, and subsequently in the next few lectures we shall see the H infinity synthesis problem, which sort of forms like the pinnacle of robust control. Okay. So before we get started today, let me just quickly recapitulate some of these results, because I understand they tend to get a little too algebraically involved, so much so that we tend to lose a sight of the big picture. So what have we tried to do here? If you now focus on the screen, this is the theorem. We call it a theorem. Of course, this is not really a major theorem, but what it says is that if you have this G and the controller in this standard feedback configuration, then whatever will be the norm of that feedback system, it will be the same if you had just sort of flipped the inputs and outputs at the plant and controller terminals, both of them. So you take this G prime and K prime, G hat prime and K hat prime, it would have the same norm exactly. And this has got everything to do with the fact that the way to evaluate the norm goes via the route of evaluating the observability and controllability gramian. So when you use the controllability gramian, you are concerned with the trace of C x C Hermitian, where x is the observability gramian, and if you go via the controllability gramian, then it's C x C Hermitian. If you go via the observability gramian, it is B Hermitian y B, where y is the observability gramian, right. So in other words, no matter which route you take, you will end up with having the same norm of the system. They are one and the same, yeah, by obtaining the trace of the corresponding gramians sandwiched between either the B and B Hermitian or C and C Hermitian. So that is what we have seen earlier. Now this result should therefore come as no surprise. But the even bigger result, or the more important result that we saw prior to that, we will not go through the proof because we have spent considerable time on it, but even the main result actually takes quite some time to digest because it has got so many of these things. So let us quickly recapitulate what these subparts or these clauses entail. So, you have a standard system given like so, which is G hat, as you can see here. All that we are asking is that A, B, I, C, I, where I could be 1 or 2 are both stabilizable and detectable. And then you have this condition on the D matrix, that is the D12 Hermitian multiplying C and D12 gives you 0 and identity, which basically says that D12 Hermitian D12 is identity, and D12, the columns of D12 are orthogonal to those of C, right. That is what this says. So, if that is, these are the conditions that are met in general, then we can design some controller K hat, which is an internally stabilizing controller for G, and the closed loop performance then satisfies this equality, right, and this equality follows from some orthogonality of the subspace under which we are concerned with, right. We have seen that this inner product endows us with this notion of orthogonality, which then allows us to write equalities such as these. So, of course, there are so many intermediate steps and auxiliary plants that we are defining. Remember, the original plant is this G hat. Now, in the process we say that let us compose. So, notice that what we are using to compose these new auxiliary plants, when we are composing GC hat, everything is known here apart from F. So, F is an unknown, remember that. Okay. Then we are composing this G hat TMP, once again F is the only unknown, everything else is known. So, it turns out then that we compose these two auxiliary plants where there is one unknown, which is F. So, you might already be getting the hint that F is basically something that we have to solve for, that we have to evaluate, which would allow us to design this controller in the first place. Now, we say what is this F? Now, here you see it is B2 Hermitian X. Again, B2 is something we know, but X is something we do not know, right. So, this X is something we do not know here. What is X? Now, X is given by the solution of this Riccati equation, which is constituted by the elements of the Hamiltonian HC. Now, you ask, okay, what is HC? So, the first step was what is F? In answer to what is F, we found that it is something that depends on X. Now, then we ask what is X? In answer to what is X, we are led to looking at this, what is HC? Now, what is HC? Now, we see that HC constitutes of nothing that is unknown to us. So, if I now retrace my steps back, here is how the controller design should proceed. Okay? Just cut to the chase. Here is the utility of the theorem. One thing is to understand the proof of the theorem, which is important, but it should also be apparent to you. You should not get confused in this jungle of words and variables and stuff, and so much so that you lose sight. So, here is the deal. I give you a plant G hat. So, that means I tell you what A, B1, B2, C1, C2, D12, D21 are, and I say that this plant at least satisfies these conditions. Again, this A, B1, C1 being stabilizable and detectable along with A, B2, C2 also meeting the same conditions is not very restrictive. In fact, that is the bare essential you need in order for a stabilizing controller to exist, right. So, it is not too much of a demand. We will also see that the second condition is also not very demanding, it is not a very restrictive assumption as such. Okay. Now, then what do we have? Then we want to design this K hat. So, instead of looking at this in this flow as it has been given in this theorem, the first thing we do then is basically the last variable that was defined, which is essentially compose this HC. Now, notice that while composing HC, all that you are required to know is only the plant parameters. That is, you need to know only A, B2, C1, and that is it. So, you compose this HC. What happens then? The moment you have this Hamiltonian HC, you know the Riccati operator corresponding to HC. Solve for that Riccati operator and you get X. Okay? So, given a plant, I can always find this Hamiltonian. Given this Hamiltonian, I can always constitute the Riccati operator. Yeah? Given this Riccati operator, and you know that we have already proved that given such a Hamiltonian is always in the domain of the Riccati operator, right. So, you can always get a solution X. Okay? Once you get a solution X, what do? You plug it in here, that is minus B2 Hermitian X. B2 is again known to us. So, you get F. Now, when you get F, that basically is your controller, you have the picture, right. So, how does it come out? Well, then once you have this F, you call this G hat TMP. You see again everything in G hat TMP in this particular variable here, yeah. Everything in G hat TMP comes from the plant except for this one term which is F, but this F we have already solved. from this Riccati equation, right. So, we can get G hat TMP and we can get G hat C, right. What is G hat C? Again everything here is known because we have already evaluated F, and subject to this sort of a composition and this particular structure, now we can say that, well, if you connect this plant and this controller in the feedback path like so, then here is what you get with this GC standing as a controller, here is what you get. Well, the norm, the performance norm is given by this, okay. So, now the point is that what is this K hat, yeah, what should be this K hat so as to minimize this norm, because now just stabilizing is not good enough. I mean stabilizing any F that satisfies that Riccati operator will allow you to stabilize it, no. So, this is automatically comes by default. So, how do you stabilize this and also meet this minimization of this norm of S, that is the star product of G and K hat. So, it turns out that the first term on the right is free from K. So, that means the minimization of this norm on the left hand side is tantamount to minimization of the norm on the right hand side, yeah. That is essentially the crux of the matter, right. Then we focused our attention on this particular term, this second term which is written in this light blue or whatever color you call it, I do not know. So, this light blue colored box that I put in here, yeah, this is what we are now concerned with minimizing, okay. In order to minimize this, we will require some processes, some steps. So, we did some more algebraic manipulations and I am sure that we did it in some sort of a hurry in the previous lecture. We cooked up this E hat and you might be wondering where is this E hat coming from? I mean suddenly why am I interested in something like this? It is like somebody has whispered something in my ear magically and I have come to know of it. That is not the case, right. So, let us try and understand why this E hat was important. Maybe I should have done it a little later, but it is okay. We have already derived and shown you that this particular E and K, the star product of E and K, yeah, has a norm equal to 0, yeah, where K is given by this particular controller, right. This is the controller K, okay. All right. Now, how does this help? So, notice what are we aiming to do? Let me draw a line and start today's lecture, okay. So, what are we trying to do? We are now concerned with trying to minimize the star products norm, where the star product is between G hat TMP and K hat, but okay, I can get rid of the square here, but notice that we have already shown by theorem 2 that minimizing the norm, I mean the norm of G hat K hat is the same as the norm of G hat prime K hat prime, where G hat prime and K hat prime are obtained by the transpositions and Hermitian operations on the respective ABCD matrices. So, the A goes to the A changes to A Hermitian, B changes to C Hermitian, C changes to B Hermitian and the D changes to D Hermitian. Yeah, that is how you, that is what this prime operation entails. And in doing so, we have claimed that the norm does not change one bit. So, therefore, we can now essentially turn our attention towards not just minimizing this norm. So, we are moving our or rather restating our goal, we are not moving our goal posts, we are restating our goals in a different language. So, that is tantamount to minimizing the norm of this star product G hat TMP prime K hat prime, okay. But you might wonder how does this help? So, recall maybe a previous lecture or a couple of lectures back we had defined what this G hat TMP is. Now, based on this our understanding of the prime operation, we can now say, you can please go back to the notes you have taken down in the preceding lecture to see what G hat TMP is, and then you will observe immediately that G hat TMP prime will look something like this, A replaced by A Hermitian, and of course, whatever was here in this place of the C matrix for the G hat TMP will now be replaced with the Hermitian conjugate of Hermitian transpose of the C, okay, or the B here. So, in other words, let me just write it down, because yeah, that will make things clearer. So, we will have this as minus F Hermitian C2 Hermitian. Notice that in original G hat TMP we had minus F and C2 here in this vertical channel here. So, we are just putting it above there, right. So, we are just flipping the B and C, okay. And here we have B1 Hermitian, B2 Hermitian, which were sitting in this place here in the original G hat TMP. Also, we will have 0, 0, these do not change, but now instead of the identity here, we will have the identity here, and instead of the D21 here, we will have the D21 Hermitian over here, okay. So, this is our G hat TMP prime, okay. And let us replace K hat with K hat with K hat prime, okay. So, what is K hat prime? So, then now we turn our attention to this fellow. This is what we are now going to be interested in, yeah, okay, great. Now, what do we get? In order to understand what this fellow's norm entails, the star product of G hat TMP, again you see this is totally contingent upon what we choose as our F here, right. So, maybe the F is known here, but now what are we going to decide? There is going to be something that is going to be undecided, like the unknown here, right. Remember in the previous case we had the F which was to be decided. So, now we will also have to have some other unknown here, okay. So, eventually I ended up going back after all. So, here was this unknown and GTMP, and notice that this GTMP is now the original plant, whereas in this case the original plant was this. So, everything in the original plant is known. So, now we are saying that everything in our GTMP hat is known, all right. So, then there is some unknown here. Instead of F we are going to call it G, we are going to call it L now, okay. So, we are posing exactly the same problem here. Instead of G hat here, now we will start with G hat TMP prime, okay, and apply the conditions that we had in theorem 1 exactly in toto, no difference whatsoever, because you see now that G hat TMP prime has exactly the same structure with everything being known now, because remember that F we now know, it comes from X, X comes from the solution of the Riccati equation given by elements of HC, and elements of HC are again coming from the original plant, yeah. So, everything is known here. So, what I am saying essentially now is that this F that we have here, do not treat this as an unknown now, sorry, it was much later, yeah, here. So, now this F here is not an unknown really for us, right. Now, we will have a new unknown which is L, which will be part of our GC. So, instead of calling it GC, let me call it GF, okay. So, GF now in terms of the elements of G hat TMP and an unknown L. Earlier the unknown was F, now for plant being given by G hat TMP prime, the unknown will be L. What will that L be connected with? The L will be connected with the B matrix, and precisely, to be precise, the B2 element, which is this, okay. So, here goes. Notice very carefully, A Hermitian plus C2 Hermitian L, then you have the identity here, and this is going to be B1 Hermitian plus D21 Hermitian, that is this element coming from here, D21 Hermitian L. Notice in the previous case it was D12, but now the D12 element is replaced by the D21 Hermitian, yeah, and this was 0 like before. But this is our GF prime, right, GF, right, okay. So, now that we have this, what is the other element that we have? Now, remember it is like when we had started with G, we had two auxiliary plants that we got. One was this GC hat, which is whose place is now going to be taken by this GF hat prime, not just GF hat, but GF hat prime, okay. So, what we will now do is, we will have to find the G hat TMP corresponding to G hat TMP. Sounds a little confusing, right? Let me elaborate. On the left hand side here you have G hat, from which you compose an auxiliary plant G hat TMP. Now, you just sort of cover up this entire thing, hang on, you just cover up this entire thing here, and you focus your attention only on this part. So, now to start with your plant is just this, right. So, this is now going to take the place of your G hat, or rather this prime of this G hat TMP. So, now for corresponding to a plant that is given by G hat TMP, what will be the G hat TMP now? Yeah, and this is essentially the crux of the matter, and this will tell you why in the previous lecture we devoted some time towards understanding this another auxiliary plant from nowhere, apparently this E hat. So, observe, now the things will fall in place. So, okay, let me before that, since we have already defined this GF hat, let me define GF hat prime. That is going to be A plus LC2, the I is going to come here, this is going to be B1 plus L D21, and this is going to be 0. Okay. So, now we are going to say that the norm of the star product of G hat TMP comma K hat prime squared is going to be equal to the norm of GF hat prime into F Hermitian squared. Why F Hermitian? Notice very carefully, F Hermitian is sitting in the position of B1, and in the original plant's equation, in the original theorem that is, which we had proved the other day, yes, here it is. Just a minute, oh, this is the proof. Yeah, notice that you had GC hat and B1. Now, GC hat is replaced by GF hat prime, okay, and B1 which was sitting in this location for the original plant. Now, you are starting with G hat TMP. So, what is sitting in this location for G hat TMP? Well, it is nothing but F Hermitian rather, if I am not mistaken. Let me check. Yeah. Where was I? Yeah. So, you have minus F Hermitian. So, of course, the minus 1 sign really does not matter, right, because the norm of the negative quantity, inside if you put it inside the norm is always going to spit out a positive quantity, and anyway this is squared also. So, it does not matter. Now, what does it get added to? So, that is the G hat TMP corresponding to G hat TMP, that is what I meant by it. Okay. So, this is the funny thing. How did you get G hat TMP from G hat? Now, we are going to exactly do the same thing to G hat TMP prime to get its corresponding G hat TMP. In other words, when I had a plant, notice the structural changes we made to get G hat TMP from G hat. So, what is the only thing, what are the things that differ between G hat and G hat TMP? You see, G hat had A, B1, B2, C1, C2, 0, D1, 2, D21, 0. Okay. And if you side by side place G hat TMP, A remains the same, B1, B2 remain the same. The things that change are C1 gets replaced by minus F, which is an unknown. In our case, this minus F will be replaced by L. Okay. So, that is going to be our unknown. Notice this D21 remains the same, C2 remains the same, only D12 position gets replaced by identity. So, now if I look at what the corresponding G hat TMP corresponding to G hat TMP would be, I would get the norm of the star product between E hat prime, right, K hat prime, where E hat prime is exactly what we had defined in the previous lecture. Notice what was E hat? Here goes E hat. Okay. So, observe then what is E hat prime. This is exactly what we had defined earlier. We had almost pulled it out of thin air. We hadn't given any description. I just shown you that suppose you consider this auxiliary system, and I asked you to bear with me and take some things on faith. So, now if you take that on faith, you will notice that what happens, what is sitting here. If you take E hat prime, you will get A Hermitian replacing A, yeah. This minus L and B2 will come in the place of C. So, you will have minus L Hermitian and B2 Hermitian here, and in this place of B here you will actually end up getting minus F Hermitian and C2 Hermitian. Of course, this identity and identity, it really would not matter, right. So, if you start with G hat TMP, then E hat where E hat prime, sorry I missed this prime, E hat prime is going to be given by, so look at G hat TMP, you will have A Hermitian as before, okay, all right, and you will have the B part remains the same. So, it is minus F Hermitian C2 Hermitian minus F Hermitian C2 Hermitian, okay. What happens to the C? Just a minute, yeah. So, hang on, yeah. So, let us look at how we went from G hat to G hat TMP, that will give us the clearer picture. Yeah. So, notice that the C got changed actually, the C2 position remained the same, but the C1 position got replaced by the unknown, yeah, in which case our unknown will be L instead of F, because F is known to us. So, we will replace this with minus L, and of course, this will be just B2 Hermitian like it was in G hat TMP, yeah. What happens to this? Well, this element remains unchanged, but this element has to be changed by identity. So, you will end up getting 0 I 0. So, now E hat is given by, of course, you just flip the B and C matrices with their corresponding Hermitians and flip the B, replace the B Hermitian with C and C Hermitian with B, right. The D is also replaced by D Hermitian, but then D here already you see it is symmetric, it matters not what you do, and A replaced by A Hermitian. So, A Hermitian's Hermitian is just going to give you back A, this is going to give you minus F and C2, and this is going to give you minus L. So, okay, there is some mistake here, and the mistake is that, okay, I have written down this entire thing, but earlier itself I had made a mistake. You see, it is not even matching dimensionally, right. So, there should have been a Hermitian here in the E hat prime, yeah. If you look at what this E hat system entails, right, then this E hat prime should have had the L Hermitian instead of, it should not have been L, it should have been L Hermitian, all right. So, that is where we went wrong initially to begin with, and so we needed to take this into account. Now, therefore, when you get back to this E hat, then you have the, yeah. So, now it makes sense, all right. So, you get back this E hat is equal to this minus L, yeah. So, that is actually the correct interpretation. So, I had made a mistake here, please make a note of this, all right. Yeah. So, that is a correction we need to incorporate. We already know that the norm of the star product of S E hat K hat is equal to 0. Therefore, the norm of the star product of E hat prime K hat is also going to be equal to 0, because these are after all one and the same, their norms are one and the same, right. These star products are not one and the same, but the norms are the same, as we have already seen earlier in one of the theorems, right. So, therefore, we can now safely claim that we can get rid of this term, because its norm is after all 0, right. Implies that the norm of the star product of G hat TMP K hat prime, G hat TMP prime K hat prime. squared. It matters not whether you square or not really, because there is only one term now. So, you can just take the square root on both sides. It is just going to be g hat f. Yeah, now you can apply the prime on both sides again. So, we apply the result that if you take the prime on both sides, this is going to be just g f hat f. Yeah, it will really not make any difference. So, this is what it is. So, now in view of this entire discussion, what can we claim? The main synthesis result. Now, we are in a position to summarize this. Okay? The complete synthesis result. So, what we did the other day was not really a complete synthesis result. Remember that theorem 1 what we are calling, this is incomplete in the sense that we are only concerned with the state feedback part. Okay? Here what we did was we assumed that the states were available to us for our controller synthesis. So, we can just use a state feedback, yeah, and that is it. But in general you will not be fortunate enough to have access to all the states. So, the complete synthesis will involve designing a controller based on the output that you can access from the plant and not necessarily explicit information about the states, right. So, that is why now what we will see is that there is this observer based feedback which does indeed give us this solution to this H2 optimal synthesis problem. So, here is the main result. Let G hat be the plant given by A, B1, B2, C1, C2, 0, D12, D21, 0 like so, and A, Bi, Ci for I is equal to 1 comma 2 is stabilizable and detectable. Further, suppose D12 Hermitian C1 D1 C1 D12 is equal to 0 I and D21 Hermitian C2 D21 is equal to 0 I. Okay. Optimal in the sense of H2 optimal. Okay. So, optimal controller is given by K hat is equal to A plus B2F plus LC2 minus LF0. So, now we will fill in the gaps. Okay. This once we have stated this result, the proof will really entail almost nothing. Yeah. The only thing that the proof will require us to probe is where is this L coming from, and as you might guess, just like the F came from the solution of a Riccati equation, the L will also come from a corresponding solution of some Riccati equation, some suitable Riccati equation. Yeah, and that will be mentioned in this result. So, this result basically will tell you everything that you need to know about designing the optimal controller with L is equal to minus Y C2 Hermitian, F is equal to minus B2 Hermitian X, where Y is equal to the solution of this Riccati HF, again as before, right. We are going to state this first and then we are going to explain, but while designing you will have to follow the opposite route. So, again I am just telling you right up front what is this k hat, what is this going to be this, this controller design, right. But then that really will not allow you to design it right away, because both these f and l are unknown to you. And then in the next step I say, oh look, L is this, F is this, and again you might say, okay, but what is this y and x then? So then I say y is the solution of this Riccati equation given by the Hamiltonian HF, and x is the solution of the Riccati equation given by the Hamiltonian HC. And then you ask me what is HF and HC? So this is the final step, and HF and HC had better not include anything that is not part of plant parameters, and indeed that is going to be the case. So this is what H2, you might already be able to guess what this HF and HC will look like. So HF is equal to A Hermitian minus C2 Hermitian C2 minus B1 B1 Hermitian, and this is minus A. HC is equal to A minus B2 B2 Hermitian, and then this is C1 Hermitian with a minus sign, C1 Hermitian C1, and this is going to be minus A Hermitian. Okay. So this apparently gives us the solution to the problem. Okay. So what do? You have a plant given by A, B1, B2, C1, C2, D1 to D21, where it is of course the corresponding ABC pairs, the triplets are stabilizable and detectable, and further suppose these two conditions are also met, then what is the first thing you do? Well, given based on the plant parameters, cook up these two Hamiltonians. Once you have these Hamiltonians, remember, observe that these Hamiltonians do not require anything other than the plant parameters. So cook up these Hamiltonians. Once you have these Hamiltonians, you know that Hamiltonians such as these do belong to the domain of the Riccati operator as we have defined. So corresponding to both of them, you get the solutions to the Riccati equations corresponding to these Hamiltonians. Suppose the solution corresponding to HF is given by y, and that corresponding to HC is given by x. Yeah. So then you can obtain y and x. Next step, so now basically the process is going up like this. So next step, you just plug in this y here, get L, plug in this x here, get F. Okay. And then once you have done that, all that you now require to do is compose this controller. This is your desired controller. Okay. Now that F and L are known, this is the A matrix of your controller, this is the B matrix of your controller, and this is the C matrix of your controller, and of course it is a strictly proper controller. So the D is going to be 0. Okay. And this gives you the optimal controller, but well, what is the optimal value of the performance metric? Okay. So we will not just stop at this point, we will also say additionally, if you put this controller in place with the plant and look at the star product, so additionally you will have the performance achieved is given by, so here it goes, it is the two norms of the star product of G hat, did I call it K hat or K2 hat or something, K hat, G hat, K hat, yeah. So this squared is given by equal to G hat C B1, which of course we had already seen we could not do anything about, plus we had that the star product of G hat TMP, which was an auxiliary. But then we immediately, just preceding this result, we saw that two norm of that G hat TMP could be further minimized, and in fact with this particular choice of controller, it should come as no surprise then. We had not described this part though in our previous result, so now we also outline it. This is exactly following the same line. Okay, you can just check. We are just mimicking the steps, in other words. It is just looking a little cumbersome, but we just put your head down. In fact, you can take it down as an exercise to write this logical flow in the opposite direction to get these results. Okay. So what will we get from this? So hang on. Yeah. So what we now have is plus the second norm squared of f g f hat squared, where, but of course, g hat c is exactly what we had said the other day. A plus B2F is the A matrix corresponding to it, this is the B matrix corresponding to it, the D matrix is 0 and the C matrix is C1 plus D1 to F, and GF hat is given by A plus LC2, the B matrix is given by B1 plus L D21, the C matrix is given by identity and the D matrix is also given by 0 again. Okay. So, that is it. If you put this GC, yeah, maybe just multiply with B1, whatever is the norm of that, the square of that, plus if you put this F with GF hat like so, then you sum together the square of their norms. It is like some Pythagorean identity, it looks like. Yeah, that's uncannily, that uncanny resemblance is because you are dealing with an inner product space. Yeah. So, it is basically, you know, the sum in two orthogonal complement spaces. You can take that as an exercise to check that also. Yeah, one of them comes from subspace and the other comes from its orthogonal complement. Okay. So, these are basically projections in two orthogonal complements, two mutually orthogonal subspaces. Okay. Anyway, that is a bit of a mathematical sophistication, but to understand the problem, here it goes. So, this is basically the minimum, the best controller. If you plug in this controller here in the star product on the left, the controller that we have just outlined previously, you will immediately see that it turns out to be like so, and this is indeed the minimum that you can, the best that you can do. Okay. And we have shown it is the best, because remember, when you try to minimize something, even when we were young, right. So, this approach that I have taken, if I might draw an analogy to what we have done here today, I would say it is like I give you a polynomial. Yeah. So, suppose I tell you that this is x squared plus 20x plus 200. Okay. Now, of course, if you want to minimize this polynomial, you can go ahead and sort of you know, f prime x you can evaluate the derivative with respect to this, and you can get that x is equal to minus 10, yeah, and then x is equal to, and then you go ahead and check that f double prime x is equal to 2, which is greater than 0, therefore, x is equal to minus 10 is a minima. Yeah. So, that is using calculus. But on the other hand, you do not necessarily need to use calculus, no. What you could have also done was you could have taken f x is equal to x squared plus 20x plus 100 plus 100, and you can argue that this is x plus 10 whole squared plus 100. Yeah. So, if you are interested in what is the minimum value of f x in the second approach, you do not really need calculus. You can just say this is the sum of two squares. So, put x is equal to minus 10. So, one part of it is free from x, the other part contains x. So, if you want to minimize this, you put in x is equal to minus 10, and you will see that f x min is going to be equal to 100, and that is exactly what we have done here. So, this is just kind of like a simplistic example that you are familiar with from your high school days. Yeah. And what we are doing here is exactly the same. So, we had one norm on the left hand side, we could split it up into sum of two other norms, squares of two other norms. So, all of these are positive quantities. The crux of this proof follows exactly the same reasoning as here. We can write this f x as sum of two positive quantities. X plus 10 whole squared is positive, 100 is positive. The only term that we can influence by using x is the first term, 100 cannot be influenced. So, there is nothing I can do, it is at least equal to 100. Now, can I make it exactly equal to 100? Well, if I am allowed to choose x is equal to minus 10, then I can just apply that and make it exactly equal to 100. So, that is the best I can do. So, exactly the same line of reasoning, I hope you agree that there is nothing really left to prove here anymore. Whatever was there, we have done it. Okay. So, essentially, if you ask me whether we have completed our H2 synthesis problem, this is it, we have. But I will not stop here. I will just give you another flavor, another approach towards this minimization, and I will show you how this same problem can be tackled using LMIs, linear matrix inequalities. So, the same thing we can do now using an LMI approach. So that by the time we are through with these 3 controller design paradigms, one is the internally stabilizing controller using Euler parameters, yeah, and then this H2 and H infinity, we will begin to see that, you know, when we have these optimizations, we can always formulate them as convex optimization problems, okay, and that is always a good thing because you can code them nicely in a computer as a convex optimization problem. Of course, as we will see, there is always some element of choice involved here, yeah, some artful aspect to this controller design, but then that even in a very preliminary control theory course, classical control course, you might have seen when you design these lag lead compensators, yeah, it is not necessary that forget about optimization, it is not necessary that 2 of you designing the same controller for the same plant to meet the same goals would come up with identical controllers. There is always a non-uniqueness. So, there is always an element of art, an element of choice involved there. We will see that this LMI approach also highlights that aspect in the controller design. Okay. So, now what do we do with this LMI approach? Here is what the first result. Okay. Here is what the first result states. A is Hurwitz and the norm of P is less than 1. What is P? Well, P is basically, you know, the A, B, C, D, the packed matrix notation. Okay. Okay. So, this statement that A is Hurwitz and the second norm of P is less than 1 is actually equivalent to, because look, this is all that we want to do, right. Through all this minimization problem and everything that we have done, this has throughout been our goal that this A matrix had better be Hurwitz, that is it is internally stabilizing, and we want to minimize some performance norm, right. So, minimizing some performance norm, and if you might say, okay, then what is so special about 1? There is nothing really special about 1. So, if you want to minimize this beyond a certain point, yeah, make it lower than a certain point, then scale it up, right. If you want to get fx to be less than 2, then you can actually say that I want half fx to be less than 1. It is the same thing, no. So, that is exactly the reason why without loss of generality we have put this 1 here on the other side, right. So, there is nothing other than that apart from that. So, now this problem I am sure you will agree that the way it has been stated in the first line is tantamount to what we know how we have already formulated the classical problem here. But now this turns out that this is equivalent to saying that there exists X symmetric or Hermitian greater than 0 such that trace of Cx C Hermitian is less than 1 and Ax plus X A Hermitian plus B B Hermitian is less than 0. Why is this second formulation important to us? Because this already has the makings of an LMI based formulation, you see. Yeah, this first part is exactly how we have formulated our H2 optimization problem. But the second part, if we can now show, if you can prove this result that this is indeed the same, then we can then hereafter carry on with the second line of formulating this problem, this second formulation, and say that once we have solved the second problem, we have actually solved the first problem, right. But the second problem already has inbuilt within it this LMI formulation, LMI based formulation. So, let us try and convince ourselves that this result about this equivalence of these two formulations is indeed true. So, we will first take the only if part. Okay. So, what we say is that trace of Cx C C Hermitian is less than 1 and A is Hurwitz. Yeah. This is of course true where Xc is basically nothing but controllability Gramian. So, you know that trace of C x C C Hermitian is nothing but the second norm of P2. So, the moment I am saying the second norm of P2 is less than 1, I am essentially saying that this trace is less than 1, and A is Hurwitz is just the restatement of the same fact A is Hurwitz. So, this is given to us. We have to show that it is the same as saying. So, this statement is the same as this statement, you agree, and now we have to show that this statement is also the same as what we are claiming in the second part. Okay. So, notice that let x be defined as 0 to infinity e to the at b Hermitian plus epsilon I times e to the a Hermitian t dt. Yeah. X is continuous in epsilon, and for epsilon is equal to 0, x is equal to xc. Of course, if epsilon is equal to 0, then x devolves to the controllability Gramian itself. So, it is obvious. Now, the key to our argument is by continuity. So, remember, because it is xc is the controllability Gramian, and because we know that the Planck's norm is less than 1. So, therefore, when you plug in x is equal to xc here, it is obviously less than 1, that is what we have just convinced ourselves, right. Now, by continuity, we may observe that, what do we observe? So, continuity in epsilon or epsilon, we may observe that, what can we say? The trace of C x C Hermitian is also less than 1. So, if you see x and xc are chosen to be very close to one another, they are actually related by this, no, that this is because of the continuity. If you keep changing epsilon by small amounts, x will be in a small enough neighborhood of xc. Yeah. So, if x is very close to xc, then after all this trace, yeah, trace of C Hermitian and C x C Hermitian, they are also going to be very close. So, you can always choose some x that is close enough to xc such that that fellow's trace is also less than unity. That there exists x such that this where x satisfies, hold on, what does x satisfy? X satisfies Ax plus Xa Hermitian plus Bb Hermitian plus epsilon I is equal to 0. You can just check that if you plug in this, I leave that to you as an exercise. So, you take this as Ax, Ax, so that means it is a derivative. So, Ax plus Xa Hermitian is basically nothing but a derivative of this term, yeah. So, that is basically, that is what it is, no. And then you can apply just plus Bb Hermitian, and you will see that you will be left with just minus epsilon I. Yeah, you perform the integration with the assumption that A. So, this is true, but this implies that A is Hurwitz. Yeah. So, therefore, we are done. I mean, the moment you say that the Planck's norm is less than 1 and that A is Hurwitz, yeah, this readily follows then that this becomes then, this part then becomes negative definite, no, for any small enough positive epsilon, yeah, because this is then negative definite, because this is equal to minus I, minus epsilon I, right, yeah. So, you will agree that this is indeed the case. So, we are done with the only if part. Now, we go to the if part, okay, the necessary part of this proof. So, what is given to us? There exists x such that Ax plus x A Hermitian plus B Hermitian is less than 0, and that the trace of Cx C Hermitian, which is what we have claimed as part of the second problem, notice, is also less than 1. Okay. So, this is what we have to show. Okay. And obviously, note that A is obviously Hurwitz. You must be very careful when we make claims like obviously, yeah, and ask yourself if they are indeed obvious. Why do you think A is obvious? This is obvious? Well, for one, you immediately check that Ax plus xa Hermitian. Yeah, so I would also say that maybe there exists x which is positive definite. So, the moment you have this, it means that Ax plus xa Hermitian is equal to, is less than some negative definite matrix. So, it is also negative definite. So, there exists a positive definite x such that Ax plus xa Hermitian, which is the Lyapunov equation, is negative definite. Therefore, it is obvious that A is Hurwitz. Yeah, so that obvious part follows from this observation. Okay. So, Hurwitz is given. So, notice that the first problem says that A is Hurwitz, that we have already seen. Now, we have to show that this also means that the second part of the problem is also going to follow from this. Why? Again, when x meets this condition, x is called the generalized controllability Gramian. Yeah, it does not meet the strict equality, but it is basically something that satisfies the inequality. So, what happens then? Notice that Axc plus xc A Hermitian plus B Hermitian plus B Hermitian is equal to 0, and Ax plus xa Hermitian plus B Hermitian is less than 0. Yeah. So, if we subtract the first one from the second, what do we get? We get Ax minus xc plus x minus xc A Hermitian is less than equal to 0, where notice that both x and xc are symmetric or Hermitian matrices, and this overall thing is negative definite. Yeah. So, if this overall thing is negative definite, then this, let us call this x tilde, this x tilde is greater than 0. Yeah, because that is because A is Hurwitz, right. So, if A is Hurwitz, then this x tilde is greater than 0. So, if x tilde is greater than 0, this means x is greater than xc. That means C x C Hermitian is greater than or equal to, the trace rather is greater than or equal to C xc C Hermitian, but this is in turn So, what do we already know? We know that this is in turn less than 1. This is the trace, but this is less than 1. No, this is given by the formulation of the second problem, this inequality. This means that trace Cxc C Hermitian is less than 1, implying that P second norm is also less than 1. So, that means when you have the second problem formulated like so, you already also have the first problem's conditions embedded within it. So, that means both these problems are one and the same. Okay. So, when we meet for the next lecture, we will see how this formulation, already half the game is won, as they say, because we have been able to show you that this H2 optimization problem or H2 optimal control problem has an equivalent LMI formulation, which is an exact equivalence. So, therefore, if we can now show you a method to obtain a solution for this formula, it is not really completely an LMI, it is not very obvious to see though yet, but you already see a hint of an LMI in the sense that there is an inequality. So, we will come back in the next lecture and complete the story. It will not take too long. We are almost there now. Yeah, and we will wind up with this H2 optimal control in the next lecture and show you that there does exist a solution to this problem, and then subsequently we will launch into the final paradigm, or there is the H infinity problem. So, our goal is that after we study that H infinity, we would have studied at least 3 synthesis methods: the Euler parameterization, the H2 optimal control, the H infinity synthesis problem, and then we will look at what we have promised thus far, which is uncertainties, because thus far we have only looked at optimizing some performance metric for a plant using some controller which stabilizes it. But right at the beginning of the course, we had promised something a little more. We had promised you that even when plants are not modeled in a certain manner, there are uncertainties in the plant model. Sometimes because we cannot model the plant physically very accurately, that's why that uncertainty is something we have to live with, and sometimes because we don't want to make the maths intractable. So, we want to have a tractable problem on our hands, which is why we deliberately ignore certain things to come up with a model over which we can have some handle, right. So, due to these two things particularly, we often come up with an approximate model. So, in general we can model such plants with an exact model and some uncertain part, and the moment that uncertain part comes in, we have another goal to achieve then, right. Apart from just stabilizing the plant here, we will then want to stabilize the entire family of plants. Yeah, and then also impose the condition that we will minimize, we would love to minimize some performance metric like we have done here. So, that is going to be even more interesting. So, that will entail us looking into how uncertainties are modeled in the first place, like the structured uncertainties, unstructured uncertainties, and so on and so forth. So, once we are through with H infinity synthesis, which should take maybe another 2 to 3 lectures, then we will begin our journey into looking at these uncertainties. We will also on the way take the special case of the single input single output systems with some particular kind of uncertain models like interval plants, and we will look at this celebrated Kharitonov's theorem in that context. And then the remainder of the course will just delve into those uncertainty models and how in the face of such uncertainties we can still design or synthesize controllers. So, that is what we have to look forward to in the subsequent lectures. So, till then, take very good care. Thank you.